Hello everyone. So my name's Aaron. I did my PhD here at the University of Sheffield a few years ago. I was in animal and plant sciences. I'm trained as an ecologist by background. After that I went and did a postdoc up at the University of Edinburgh where I looked at the way that climate change is impacting ecosystems in the Arctic, in particular how there's an increased fire frequency in the boreal forest, and that's changing the way in which the permafrost, the frozen soils in the Arctic, are thawing out. And then as they thaw out, that changes the biogeochemistry of those soils and the microbes and the fungi that live within them, and causes feedbacks to the climate system. So I've kind of got a background in what you would call, environmental earth system science and ecology. I'm going to kind of share some of the kind of ideas that I think are really important from that point of view, and how they can help us think about questions of sustainability in what's being increasingly known as the Anthropocene, and we'll come on to what that means as a definition in the talk. I think my interest in the environment and kind of these questions really grew out of the fact that I was very lucky to have been brought up here in the Nant Francon Valley in North Wales, just on the edge of Snowdonia. And I used to spend a lot of my free time roaming those hills, kind of getting to know the countryside, getting to know those mountains by name, and kind of that understanding really helped me see the importance of all the different natural processes going on around me, but also the very nature of the construction of that valley and how it was eroded out of that landscape kind of gave you a really sense of kind of the scale and time frames of the Earth system. And so I used to go up to the top of these mountains and admire the view, and I still do whenever I go back to visit my folks. And thinking and sitting up there kind of gives you a lot of time to kind of, like I said, think about these processes and expand your awareness of what's going on around you. And so I'm just going to go through a kind of just to demonstrate what I mean by that with you here in the room, okay? So if you'll just indulge me for a second, can you all just breathe in together? So breathe in now, and then breathe out. And just breathe in again, and then breathe out again, okay? And so by that very act, we're all connected together through the air that we're breathing and the molecules and the particles and the elements of that air that are exchanging between us and the environment that we're in. And that's true on a much grander scale, okay? So the other kind of awareness that I kind of really thinking about these things is important to understand is what's kind of could be understood as planetary awareness, okay? So what I mean by that is that if you were sat here and you're thinking of everything that's below you, okay? So all the rocks, all the soil, all the water trickling through those rocks, and all the different life forms, the fungi and the biota and the microbes that are living within that surface. But if you keep going down below that and below that, you'll ultimately end up at the core of the Earth, right? Which is 4,000 degrees and completely inhospitable to life, right? It's really hot and dead, okay? And if we were to look the other way and look up above our heads into the sky, there'd be birds flying around, there'd be crows and seagulls, and if we looked further than that, there'd still be microbes and pollen and spores blowing in the winds far above our heads. But if we went a bit further than that, we'd be in empty space, and it would be cold, and it would be dead. Okay? So when we first kind of fully grasped this idea, I think, was when astronauts left to visit the moon, all right? And what they found was most interesting when they were visiting the moon was not the moon. The moon was lifeless and dull and barren, but the Earth was beautiful, right? And it shone in space, and they couldn't quite explain how much that experience kind of transformed the way that they thought about the world. But I think increasingly we are thinking about that in those ways as well, as these kind of photographs become more common. And actually, this one's even more amazing, I think. So this was taken by Cassini, a probe that was sent to visit Saturn. Again, on the way there, as it arrived at Saturn, it turned around and it took a picture of where it had come from. All right, that pale blue dot there is our home. That's the Earth. floating in space, that one little pixel. And I think, when you understand that, you understand just how special the Earth is, just how unique and fragile that home of ours is. And so when you look at this picture of the Earth, you see it as a whole, right? You see it as a connected system. You see everything that we ever loved or cared about there before our eyes. And there aren't any borders or boundaries. Everything's just connected and flows together. And so that's what we mean when we talk about the Earth system, okay? This connected whole, that there's all the processes that go on that support life on this planet. So this is a video that was produced by NASA, just to give you, I think, a more in-depth feeling of what that's about. So this is a simulation where they look at different aerosols in the Earth's atmosphere, and you can see them swirling around and being produced by different Earth processes. So what you can see is all these different colours. So they're the different aerosols. So there's this white one is sea salt. You've got these kind of yellow ones are sulfur. The red ones are fires, and you've got this orange dust here, which is dust blowing off the Sahara and transporting nutrients all over the Earth, right? So what this next one is showing you is hopefully going to work. So these are different satellites studying the Earth from space, and they're showing you different properties. So this was looking at sea surface temperatures and currents. This is looking at kind of the optical imaging. This is looking at carbon being breathed in and breathed out of the plants as they're growing around the planet. This is looking at soil moisture and how much water is in different levels of the soil. This is looking at where the rain's falling around the planet. This is looking at different clouds and cloud movements. This one's looking at where the rain is falling. And that one, again, that's the winds and where we're seeing different winds, right? And we can study this all using satellites and data that we're collecting from space, right? But what it shows you is that there's lots of different processes going on, and all of those are contributing to what is a collective whole, right? The whole Earth system. And so by understanding how those different processes link together, we can understand how the Earth works. So what Earth system science does is try and understand how this collective whole is built up from different parts. And so what's typically understood is that there's different spheres of the Earth system. So there's the atmosphere, which we're all familiar with, above us, the clouds, the air, the sky, and that includes the climate processes and things like the jet stream and things. Next to that, we've got the hydrosphere, so that's the rain, rivers, the oceans. Then we've also got the cryosphere, which is ice, so the sea ice in the Arctic, the Arctic and Antarctic ice sheets, and all the glaciers in different mountain ranges. Then we've also got the lithosphere, and that's talking about all the rocks and the rock cycles. So erosion, volcanoes, plate tectonics, and the like. We've also got the biosphere, so that's all of life. So all the kind of plants and animals, fungi, microbes, and those carry out important processes that kind of transform nutrients and energy and feed those into those systems. So all of those things are important. And we learn about this at school, right? We learn about the water cycle and the processes of evaporation and condensation and rainfall and river runoff. We also learn about the carbon cycle and how plants breathe in carbon dioxide and turn that into energy, and then release oxygen, which animals breathe in and use to burn the energy that they can consume when they eat plants and respire CO2, making a cycle, right? There's other cycles like the nitrogen cycle or the phosphorus cycle about important nutrients that plants need to grow. And again, those are kind of transformed from being in an inorganic state in the natural environment to an organic state in the kind of the living environment. And so all of these cycles and processes are going on all the time around us, connecting both the physical and the living world together in all of these different in all these different spheres of the Earth system, right? And core to all of that is kind of the living systems, right? What's typically referred to as nowadays biodiversity by scientists, but really what they're talking about is all the plants and animals and fungi and microbes and all the interactions between those. And why this is so important is because if we think about, say, a tree growing in a tropical forest, so that individual tree will be, breathing in CO2, it will be turning that into energy to grow, and using nutrients from the soil, and the soils will be being supplied by microbes that will be breaking down other plants and other organic matter, and the trees will require pollinators such as insects or bats or hummingbirds in order to pollinate them, and then those flowers and fruits will have to be dispersed, and the seeds will have to be dispersed often by mammals and things like that throughout the forest so that they can continue the life cycle. So all of these individual animals and plants will be living out their own unique ecological niches, but contributing through that to these processes that sustain the ecosystems and keep them going. And if you scale that process up over the hundreds of billions of trees that there are in a forest like that, let's say across the whole of the Amazon watershed, what you start doing then is affecting the entire processes of the Earth system in terms of where carbon is going and where oxygen is being produced and where water vapor is being released. So over the course of that whole vast area of the continent of South America, suddenly you have a forest which is drawing up water together from this basin and putting it into the atmosphere, where it changes the climate over the whole area because it causes rainfall, right? It's storing up the water from its roots, transpiring it into the atmosphere, where it then falls out again as rain. And that cools down the forests and replenishes the water in those forests. And by doing that, it allows the rainforests to thrive and to succeed and to be passed on, right? And so this process of life is completely changing the way in which the Earth system works. And this has been true going back, the entire history of the life on Earth, going back hundreds of millions, billions of years. And we know about how the Earth has evolved and the creatures on the Earth have evolved, but as they've evolved, they've become able to carry out new ecological processes. They've formed new interactions between each other, and life has become more complicated and more diverse. And therefore, the systems have become more complicated and more interesting. And, and we're all aware of, the history of the transition of plants going out from the oceans onto land about 400 billion years ago, followed by insects and amphibians, followed by periods of reptiles, and then the dinosaurs, which were wiped out in a mass extinction by a meteorite collision, and then the mammals evolving into all their different types of forms up until the present day, right? And if we were just to focus on not that entire vast history of hundreds of millions, billions of years, but just the last period in which humans evolved, the last part known as the Pleistocene. And the Pleistocene is really interesting, not only because that's when we evolved, but also because it went through a series of ice ages. Now, this is data that's been taken from ice cores in Antarctica and Greenland, where we can understand, by drilling down into the depths of the ice cores, we can find out what past climates look like at different times. And we can reconstruct from those ice cores what the temperature was and how that fluctuated over time, and also what the level of CO2 in the atmosphere was at the different times. And we know that because of when the ice is formed in these places, it traps bubbles of the atmosphere in that ice, and we can analyze those bubbles to find out what the concentration of CO2 was going back hundreds of thousands of years. And so this time frame goes back 400,000 years, and what you can see if you look at the red line is that you get these seesaw jagged spikes where you get an increase in temperature and then a gradual cooling and then another increase. And the difference between the maximum of that, which we call interglacials, when the temperature of the planet was warmer, less ice existed on the planet, and therefore sea levels were much higher because the ice had melted into the oceans. And the minimum, which is the maximum the glacial extent, when again lots of ice was trapped on ice sheets and the sea levels were much lower than they are today, is about 4 degrees Celsius. Okay? And what you can see is that they oscillate on about a 100,000 year time cycle. And that oscillation is caused by changes in the Earth's orbit as it goes around the sun and the brightness of the sun over that period of time. And so what happens is that there's a feedback, a very strong feedback between the temperature and CO2, such that as the temperature increases, the levels of CO2 increase rapidly. And because CO2 is a greenhouse gas, that means it traps heat in the Earth's atmosphere, it accelerates the warming further, which releases more CO2, which causes more warming, and you get a feedback process which moves the Earth from one state, a cold state, into a warm state. And that oscillation happens, like I said, on a roughly 100,000 year time cycle. So if you were in my valley, the Mount Francon, 20,000 years ago, at the maximum extent of the last ice age, you'd have seen an ice sheet like this. So you couldn't have lived in that valley, which was my home, right? Because it would have been under almost a mile of ice. And you'd have just had just the peaks of those mountains sticking out through that ice. Now, that was just part of a massive ice sheet that covered the whole of Europe, Scandinavia, and into Russia. And then below that ice sheet, you had a tundra, which is covering most of what we'd now think of as France and Central Europe today. And below that, you'd have the coniferous forests in Spain and Italy and Greece. And we associate those now with the far north in Siberia and the Arctic Canada, right? The boreal forests. So everything was very, very different just 20,000 years ago, dramatically different. And that was a temperature difference of about 4 degrees between now and then. So that's the kind of changes that the Earth system can undergo. And like I said, the south of France would have looked a bit like this. You'd have had reindeer and giant mammoth and ox feeding on a cold, frozen tundra. And we were there too, right? We were living in the caves of Lascaux and other areas. And these cave paintings show just how intimately connected we were with all of this life around us and following the herds of reindeer as they migrated across the northern steppe. But humanity had changed very, very little since we emerged. Modern humans evolved, we think, about 200,000 years ago. And over that period of time, throughout the ice ages, we changed very little in terms of our technology and our ability and our culture. And so we used things like these hand axes that we made from stone, and they stayed virtually the same for that entire 200,000 years. They've changed very, very little. And yet, something very strange happened about 10,000 years ago. All right? We started the process of civilization. And that happened to coincide with a very unusual period in the Earth's climate, in the Earth's system. We entered what's now known as the Holocene, which is the last 10,000 years, and we left the Pleistocene and the Ice Age cycles and entered this period of unusual climatic stability, which allowed us to predict what the climate was going to be like, where the sea levels were going to be, because they stayed pretty much constant throughout the entire period of the Holocene, whereas before they'd been fluctuating all over the place. And we were able to say what was the rainfall going to be that year, and how high would the floods be, and that would allow us then to predict when to plant and where to plant. And so we could begin the process of agriculture and favouring the cultivation of foods that we wanted, rather than constantly foraging and moving around. And so that allowed us to start building settled cities. So the energy surplus that we got from the process of agriculture allowed us to develop more complicated civilizations. And that went on for a really long period of time as well, until we reached a point only about 400 years ago, when in Europe there was another period of climatic instability, which was only local, but we refer to typically as the mini ice age. And that caused a lot of disruption and kind of forced people to kind of come up with new ideas and new ways of living. And part of that was a kind of the creation of the printing press and how we were able to share new ideas, but part of it was also turning to study nature to see how we better can work to live in this changing world. And obviously part of that was the kind of creation of new machines, such as designed by Da Vinci in these sketches. And just 200 years after that, we entered what's known as the Industrial Revolution. And obviously, what happened there was that we discovered the ability to harness energy from fossil fuel stores, from plants and animals that had lived hundreds of millions of years ago and had been laid down over vast millennia, right? And we were able to access all of that energy which had been trapped over really long periods of time and use it very, very quickly. And that allowed us then to power into a new form of civilization and a new mode of production. So that happened here in Sheffield, obviously, right? So the steel mills were able to produce new hardened materials because of the ways in which we could use the blast furnaces, because of all the extra energy we got from burning coal. And that allowed us to build tougher steel, which allowed us to build railways and steam engines and bridges and all the rest of it. And over that period of time, we were able to build increasingly complex societies and cities and benefit in all the ways that we know. So all the different forms of infrastructure in terms of supplying water, supplying heating, supplying sewage treatments and healthcare systems and education systems that we all benefit from today. And that's true around the world, right? The last 50 years have seen a tremendous advancement in human prosperity, whether or not it's access to drinking water, medicines and healthcare systems, access to education, and the fact that the vast majority of boys and girls around the world now receive a secondary education and are literate and are able to study and have all these opportunities because of that. And the fact that we live now to much older ages and health, and the vast majority of people in the past would have died in childhood, and that is no longer the case around the world. So we are living the last 50 years probably in the best time to be alive as a human being in many ways. We've had this huge advancement in success and prosperity. And we can see that going forwards in the next 100 years, the main challenge will be making sure that the rest of the world sees that too, right? That there are still huge problems and inequalities in the world that need to be addressed. And you can imagine, we still struggle to supply, healthcare and education and the governance of that in our country, and we've been doing it for 100 years and we had a huge head start on many places. Imagine if you're trying to govern a city which is growing at a rate of 100,000, 200,000, even 300,000 people a year in some places. How do you make sure that they all have access to healthcare, infrastructure, water, education? The challenge of that is immense, and that will be the challenge of the 21st century. So we know what we have to do. And you can see what's been happening, right? This huge transformation that's happened in just the last 50 years, okay? It's completely different to the rest of all of the time that humans have been on Earth, right? So here we've got a graph at the top of the world population, and that's increased from 2 billion in 1900 to over 7.5 billion today. And it will carry on probably increasing to about 9 or 10 billion by 2050. So that's increased by over threefold in just the last 100 years. GDP, which measures wealth to a certain extent, has increased sixfold in the last 100 years. Or the urban population, or energy use, or fertilizer use, or the number of large dams, or water use, or paper production, and transportation use, telecommunications, international tourism. All of these are following that huge acceleration, that exponential increase. Okay, and that's what has, in many ways, delivered the success that we've experienced. But at the same time, we are now seeing similarly large exponential increases in perturbations to the Earth system. So the increase in CO2, nitrous dioxide, methane, the loss of the stratospheric ozone layer, the surface temperature of the planet increasing because of global warming, the oceans becoming more acidic, the number of fish that we're catching, the number of shrimp that we're farming, the amount of nitrogen that runs off into the oceans around our coasts, tropical forests being lost, domesticated land increasing, so you get the idea, right? So these things are all changing dramatically too. And from what I was describing to you about the Earth system, you should have some expectation that this is going to have consequences for humans and how we live on this planet. Okay? So if we look at deforestation, since humanity began the process of civilization, we have lost about half of the world's trees. Okay, half of the forests have gone. We have built large dams on most of the world's rivers. We have mined for all sorts of resources. This is a gold mine in Australia. This is a lignite mine in Germany, mining for brown coal with one of the world's largest machines. Those dumper trucks are still far larger than, you know, an average truck. It's absolutely ginormous. This is combine harvesters farming in the Great Plains in the US for miles and miles and miles. The water extraction in the deserts and the ways in which we can use irrigation in order to grow food in places historically we'd never be able to, by mining for water from aquifers. This is what's known as a concentrated agricultural production zone, or a CAFO, in the US. So here what you're seeing is pens of cattle, right? And they don't graze, they just get fed corn and other grain. And then what you're seeing here is all the runoff, the sewage, the urine and the feces being washed away into these holding ponds. Okay? And some of that then leaches into rivers. And so this is the Gulf of Mexico off Louisiana, and you can see the Mississippi going in through New Orleans. And what you see there is an algal bloom caused by all the extra nitrogen that's now entering the system and changing the ecological processes. And what that does is that the algal bloom, when the algae have finished growing and start decaying and dying, the bacteria that break them down use all the oxygen that's in the water column. And that then creates what's known as a dead zone. It basically, anything swimming into that area will become asphyxiated because there's no oxygen in the water there. So we have changed the way that the world is working dramatically. So the amount of CO2 in the atmosphere has increased by 45% since the Industrial Revolution. We are fixing twice as much nitrogen every year as all the world's processes does combined, right? We are now mining more material than is transported by all the world's rivers combined on an annual basis. So, in a sense, we are now a force of nature as humans. We are changing the way the world works around us. And so scientists have said, this is a whole new change to the way that the world system is working. And they've called that new way that it's working the Anthropocene, right? The age of humans. So as to kind of show kind of another break in the kind of succession of epochs in the Earth's history. And scientists are increasingly concerned about these changes because we are so intimately dependent upon civilization, which is dependent upon agriculture, and agriculture is fundamentally about plants growing, and that depends on the Earth system. So they started saying, well, you know, are there any limits to what we can do to the Earth system before we trigger, you know, tipping points in that system? And they said yes. They called them boundaries. They said we're going to identify 9 different planetary boundaries around the use of fresh water or land or biodiversity loss or the reduction in stratospheric ozone or climate change, ocean acidification, etc. And so they looked at each of those issues and said, well, what do we think is a threshold beyond which we don't want to go? And what they found to their dismay is that we'd already exceeded at least 3 of those different thresholds in their opinion. So when it comes to the nitrogen cycle, when it comes to biodiversity loss, a lot of conservation scientists say that we're now living in the age of what they call the 6th mass extinction on Earth. So the last time there was a mass extinction was when the dinosaurs were wiped out by a meteorite. Right? It's heading in that direction, that we're going to lose so many species because of the actions that we're carrying out, and that has knock-on consequences for the way that ecosystems function. And also climate change, right? The way in which we are changing the Earth's climate, which is connected to so many of the other of the Earth system processes. And I'm going to spend the rest of the talk just looking at that issue, the issue of climate change, and looking at how we are exceeding that boundary and what that means for us. So this is another data product from NASA. It looks at the Earth's temperature over the last 120 years or so, from the 1880s until now. So the blues are cooler than average for a given location, and the reds are warmer than average for a given location. And if this works, you can see from year to year it varies. So sometimes a place is warmer than average and sometimes it's cooler than average. That's just weather, okay? But over time, it warms up and it becomes hotter and hotter and hotter and hotter. And in particular in the Arctic, right? It's warming about twice the rate in the Arctic as it is elsewhere. And if we carry on warming, we shall follow so this is the last, since 1900 till the present day in black. If we carry on burning fossil fuels at an increasing rate, we'll follow this red trajectory, okay, and that will take us to about 4 or more than 4 degrees of warming by the end of the century. Now remember I told you earlier that the difference between an ice age and an interglacial was 4 degrees. So we're going to go as much difference between those two states in the other direction. Alternatively, it's been proposed that we might be able to hold the temperature of the planet to 2 degrees. That's this blue bit here. Or somewhere in between, right? And on top of that, I've put some of my own family background, my family details, right? So my grandmother was born here in 1923. And my mother was born here in 1958. And that's when I was born in 1986. Hands up who was born after February 1985. Okay, that's most of us. Now, none of us have experienced a single month of our lives where the global average temperatures was less than the 20th century average for that month. So we were born into a different climate to the one in which our parents and our grandparents were born into. And it's only going to get more different from that. So I don't have a child, but if I was to say have a child this year, born in 2018, then here's when they would finish high school. Here is when I could expect my first grandchild to be born. And here's when my child would retire. Okay? So within their lifespan, they would see a vastly different climate to anything that I've ever experienced. And that's your lifetime, right? That's when you're going to be living through. So we have this choice about where we end up. But if we carry on this 4 degrees trajectory, and that's what that looks like in the context of the last 10,000 years. Okay? We can completely leave behind the climate of the Holocene, the climate to which the whole of human civilization is adapted to. We have placed all our cities on the coasts because that's where our ports could be, and yet the sea levels are going to change. We have based all our agriculture around the places where we know we get reliable rainfall or that there's glacier melt that will sustain them through the summer. But that's going to change. Okay? And it's going to change in ways that we're not even quite sure about. It's unpredictable. And it's going to change at rates at which we're not sure about. It's unpredictable. But we know it's going to dramatically change. And for that reason, our leaders, this is Ban Ki-moon, who was the former head of the United Nations, saying that this is an emergency. And for emergency situations, we need emergency action. And he's saying that as a political leader because that's what the scientists are saying. So this is James Hansen. He is the former director of NASA's Goddard Institute for Space Studies. And he was one of the first scientists to really warn of the impacts of climate change back in the late 80s. And he's saying, look, we are in a planetary emergency. Lonnie Thompson, director of the Bird Polar Research Center, he was one of these scientists who studies these ice cores from Antarctica and looks at past climates. And he says, virtually all of us are now convinced that global warming poses a clear and present danger to civilization. By which he means Earth system and climate scientists. So What's particularly concerning about the way that the Earth system changes is not necessarily the changes to the mean temperatures in any given place. It's how those changes in the means affect extremes. So, because it's the extremes that we care about in terms of what our infrastructure can tolerate. So this graph shows the distribution. So we've got here in white kind of the average temperature, and in red kind of the warmer than average, and blue is colder than average, right? So what you can see here is this is the temperature climate in the 1960s through 70s, 70s through 80s, 80s through 90s, into the 2000s, into the 2010s. Okay? So we're getting far, far less of these cold temperatures now, and far, far more of these extremely hot temperatures. Okay? And these almost never used to happen. And now we're seeing them all over the place, all the time. You hear about it in the news, about the heat wave, the deadly heat waves in different places around the world, right? So this hot extreme, which used to cover much less than 1% of the Earth's surface during the base period, now typically covers about 10% of the land area. And that's going to just keep increasing as we carry on warming the planet. So what does that look like for us? So in 2003, there was an extreme heat wave that struck Europe. In particular Paris and parts of France, and it was estimated that about 15,000 people died, extra deaths in France that year because of that heat wave. Across the whole of Europe, the estimate's more like 70,000 excess deaths because of the heat wave. Now, that's the 2003 heat wave. You can see just how unusually hot that was. That was completely unexpected. We'd never seen anything like it. But by 2040, in your lifetimes, that's going to be an average temperature for a European summer. And by 2060, that will be warmer. Well, most summers will be warmer than that. Okay? It's fundamentally going to change the way that Europe looks. So this is from the World Health Organization. They said in 2008, climate change will affect in profoundly adverse ways some of the most fundamental determinants of health. Because fundamentally, we are dependent on the Earth system and how it functions. And heat waves don't just affect us as people, they also affect the systems, the ecosystems of the Earth and that we rely on, right? So this is looking, this is some data from NOAA, carrying out warnings about heat waves in the oceans. And the reason that they're concerned about this is because these heat waves can really negatively affect coral reefs. Now, coral has a stress response to warming. So here you can see a normal coral, a healthy coral, and this is exactly the same coral, but after a period of what's known as bleaching. Now, what happens is that the coral itself, as an organism, is really a symbiosis between two types of organism. The coral is a type of animal with a calcium skeleton, and it also lives in symbiosis with a type of algae. And the coral provides a secure, safe home for the algae, and the algae provides food to the coral. But when you get a heat wave, their relationship breaks down, and the corals expel the algae into the ocean. And as a result, it has nothing to feed on and starts to starve. Now, it can do that okay for a short period of time, but if that heat wave continues for too long, then the corals starve to death. In 2016, as was predicted by NOAA in that warning, there was a mass coral bleaching across vast areas of the world, and in particular the Great Barrier Reef. Now, this is a flight that was carried out by a professor from the University of Queensland, and he toured the whole Barrier Reef looking at which corals were bleached. And this is what he saw for miles and miles, right? Was these coral reefs just completely bleached. And that went on and on and on. And the next year, they had a similarly hot heat wave consecutively. And 50% of the corals have died in the last 2 years alone of the Great Barrier Reef. So what's happened is that we've reached a tipping point for the coral reef ecosystem. It can no longer survive in the new climate. And this is quoting one of the world's experts on these coral reefs, Professor Ove Hugh Goldberg, from the University of Queensland. He says, "I think that 20 years from now, every summer will be too hot for corals. They will disappear as dominant members of tropical reef systems by 2040 to 2050. It's hard to argue it any other way." So corals are, in a sense, a canary in the coal mine, right? They are sending us a very clear warning about what's to come if we don't take action. It's in a way, to a certain extent, maybe too late to save coral reefs now. And that's a huge problem, because fisheries around the world depend on these reefs. The reefs are where a lot of the fish go to lay their eggs, their fry, and they act as nurseries for huge numbers of fish stocks. And this is a photograph of some Indonesian fishermen, but the same is true for many other countries, where they rely on the productivity of the reefs in order to sustain their fisheries. And it's estimated that up to about 90% of all the protein consumed in Indonesia and in the Philippines comes from fish caught from reefs. So that's going to be a huge problem for the health of people in those countries in terms of where are they going to get the protein for their diets from. So going away from the tropics now, up to the poles, there's other tipping points that we can see happening there. This is a satellite photo of well, it's a reconstruction, but it's of the polar ice cap in the North Pole. And that's in 1979. The yellow marker shows the extent of that in 1979, and what you can see is just how much it's reduced between 1979 and 2012, when we reached the current record lowest extent at the end of summer. And it's lost about half of the area of that ice cap already, and it's lost even more in terms of the thickness and the volume of the ice. And that's really important, because as the ice retreats, you expose what was previously white and reflective, and the sea ice would reflect about 80% of all the sunlight that hit it back into space. It becomes dark water, and dark water absorbs about 80% of the sunlight that hits it. And that causes it to warm more, which causes more ice to melt, and you get a downward spiral whereby you lose in increasingly large amounts of the ice. Mark Cerise, who's director for the National Snow and Ice Data Centre, says that we may lose the summer ice cover as early as 2030. This in itself is much earlier than projections from nearly all climate model simulations. So these things are happening faster than we'd expected. This is a graph of the loss of mass from the Greenland ice sheet, and you can see that that too is decreasing exponentially. And so this is a professor from the University of Irvine in California, and she says nobody expected the ice sheet to lose so much mass so quickly. Again, these processes are happening faster than we'd expected. And that's important. So the loss of ice from Greenland is having a consequence on what we call the AMOC current, right? It's also part of it's referred to as the Gulf Stream. And what this video shows is that current moving warm water from the tropics up through the Atlantic, across over to Europe, and then it hits this point near Greenland and starts going down and back under the water deep in the ocean, right? It's known as the thermohaline circulation. And that transports lots of heat from the tropics up to Europe and keeps us having these mild winter compared to, say, the other side of the Atlantic at the same latitude in Nova Scotia, for instance. So these currents are really, really important to us. And yet, because there's so much fresh water going in off of Greenland, cold fresh water, into that region of the Atlantic in the north, just where the current starts going down, it actually changes the buoyancy of the water and slows it down from falling, and that slows how much water can be drawn up behind it. So this conveyor belt is slowing down. And this new paper came out recently showing just that effect, right? We've actually, in just the last 50 years, reduced the amount of heat being transferred across this current by about 15%. Now, that's a huge change. It's during that period of time. So, and the consequence of that as well is because it's slowing down, more heat is being left in the tropics and off the coast of the US seaboard. And that's having an effect on the power of storms that are coming off cyclones and hurricanes into that part of the country. And also, going forwards, is going to accelerate the amount of sea level rise that they see in those areas. And there's a real concern amongst climate scientists that there's a tipping point here at which we slow down the current enough and it just shuts down altogether because it can no longer draw up enough heat behind it. And that would have a profound change on the Earth, on the climate in a country like Europe, right? You would actually see quite a significant and dramatic cooling in our areas over winter, but the consequence of that would be an even greater warming in places like the tropics. If we looked at the other end of the planet, Antarctica, the currents there are having a similarly dramatic effect. And what's happening is that there's increasingly warm water currents coming up against these marine ice sheets in West Antarctica. And they're retreating. These arrows show how fast they're retreating, right, relatively. And they're retreating very dramatically there. They're also retreating at this part of the East Antarctic ice sheet, even as they're advancing a little bit in the north, but only a little bit. And that's really significant because the West Antarctic ice sheet, we think, is also quite unstable. So hopefully this video will work.
We are heading towards a particular sector of West Antarctica draining into the Amazon Sea. This sector is drained by 6 glaciers. The biggest ones are Pine Island Glacier and Thwaites Glacier. The speed of the glaciers measured by satellite is shown in color code. Red is fast, blue is slower, and green is the slowest. The glaciers flow into the sea and form floating extensions called ice shelves. Now in red are the areas where the flow speed is increasing almost every year. The darker the red, the more the glacier has been speeding up. You see that all the glaciers are speeding up. Now we focus our attention on the Smith Glacier, which is a smaller glacier, but which has experienced some of the most dramatic changes. The grounding line of Smith Glacier in 1996 is at the transition boundary between the blue color, the ice shelf, and the white color, ice resting on the continent. Now we transition to 2011. The grounding line is 35 kilometers farther back, a retreat of nearly 2 kilometers per year. If we could peel off the ice from the continent and see the bed, this is what it would look like. The arrows indicate the flow direction of ice. Their color indicates the speed. Blue is slow, red is fast. We see that the glaciers flow on top of major subglacial valleys colored in brown. The darker the brown color, the deeper the valleys. As the glaciers retreat, they will follow these deep valleys. There is no mountain or big hill along the way that could act as a barrier to hold these glaciers back. The glaciers speed up, the grounding line retreat, the deep valleys that are sloping inland all reinforce each other to make the retreat of ice in this part of Antarctica unstoppable. And we think that this is what is happening right now.
So that was a study that came out in 2014. And what we're seeing is this is the increase in sea level rise around the world. So sea levels are rising and they're doing so exponentially, right? So as more and more water is coming off these ice sheets, the sea levels are rising more and more. And if we project that forwards into the future, what we're expecting to see is that if we carry on business as usual, fossil fuel pathway will follow this red one. And that's predicting that we'll see at least 1 meter on average, or maybe even up to 2 meters of sea level rise by 2100. Or if we follow this 2 degrees pathway, then we might be able to stop it at about 0.5 meter sea level rise in that period of time, but it will carry on rising for centuries after that. And that's compared to the previous kind of more conservative estimates from the IPCC. So this is more recent, and it's saying that they're underestimating what could happen, partly in response to new discoveries about what's happening in Antarctica and things like that. So what would 1 meter sea level rise do? Well, this is a study just from looking at what would happen to New York and Manhattan. So a 1 meter sea level rise could raise the frequency of severe flooding for New York City from once per century to once every 3 years. Now, we've seen what a once in every century storm looks like when Hurricane Sandy struck New York in 2012. You know, massive impact, huge, both in terms of the loss of life, but also the financial damage to infrastructure and the running of the city. So, you know, all of the subways in those areas were flooded. You also had whole neighborhoods knocked away by the storm tides and lost, you know, things like the ends of these piers and things. It was an absolutely ginormous impact on the city. But it's not just cities like New York and also many others, including, Miami and, parts of Rotterdam, London, all of them around the world are going to be affected by this. But it's all countries, right? So this is Bangladesh. This is the current sea level rise level today. The dark colour of green is mapping areas of high population density. And this is showing you the area that would be submerged by 1 meter of sea level rise. That's going to displace about 15 million people. And if we get 1.5 meters of sea level rise, it'd be close to 20 million people. So that's going to be an absolutely dramatic change for very large populations of people all over the world. And how they're going to adapt to that and deal with that is going to be, again, a major challenge if we don't reduce the rate at which this is happening. And I've put this in because I think, you know, looking at just those abstract maps can be quite kind of hard to understand what that actually means at the personal level, because, you know, it's already happening today that people are losing their livelihoods, losing their homes because of the impacts of sea level rise. So just to summarize all of that, climate change has been described as the biggest human rights issue of the 21st century by the UN High Commissioner for Human Rights, right? But it's also been described as the greatest environmental threat ever faced, the biggest global health threat of the 21st century, that it presents security challenges of a magnitude and a complexity that have never been seen before by NATO's Secretary General, that it is the greatest threat to sustainable development, and that it is the greatest failure of market failure the world has ever seen by Lord Nicholas Stern, who was a climate economist to Tony Blair and Gordon Brown's government and wrote a big report on the economics of climate change. And he's saying that fundamentally our system is failing to address this issue. So, you know, climate change is not one thing, it is all of these things together. It's not just an environmental issue, it is an issue that affects the whole of human society, because fundamentally society relies on a stable climate. And likewise, you know, in order to achieve a safe climate, we're going to have to radically change how we order society. So the world has got together to agree. So this is showing you how different impacts from climate change, so the risk to unique systems like coral reefs, extreme weather events, or large-scale tipping points like the ones I was telling you about, the Gulf Stream shutting off or the collapse of the Antarctic ice sheets, right? So that's guardrails saying we can't warm by more than 2 degrees because we risk triggering those, right? And so what this is saying is that we can accept a certain level of risk. And again, you have to ask who that's for, because obviously there's people in the front lines today who are already suffering, and I don't think they would say that those risks were acceptable. But the world has agreed that there's a certain level that we just can't avoid, right? But we have to stay below 2 degrees. So that's our choice. You know, it's getting off that red trajectory and onto the blue one. So what would that look like? Well, in order to meet that 2 degrees target, we've got to rapidly reduce emissions. So this is measuring global carbon emissions. And if we'd peaked our emissions in 2011, we'd have had to bring them down along this green curve to being at about 80% reduced by 2050. But we didn't. We carried on emitting more and more greenhouse gases. So if we'd peaked in 2015, we'd have had to bring them down along this blue curve and be at 0 greenhouse gas emissions by 2045. It doesn't look like we've peaked then either, but if we wait to 2020 to peak emissions, we've got to come down even faster to be at 0 by 2040. The reason for this is because the more that we put out now, the more we have to cut emissions in the future, right? Delay doesn't help us here because it's the total amount of carbon that we burn that actually determines how much warming we see. And if we burn more now, it means we can burn less later. So this rewrites the chronology of climate change from these long-term gradual reductions to urgent and radical reductions happening today. And if we carried on warming to 4 degrees, there's a very good chance that we would not be able to adapt to that. So this is Professor Kevin Anderson, who spoke to this society before, and saying that there is a widespread view that a 4 degrees future is incompatible with an organized global community. It is likely to be beyond adaptation, is devastating to the majority of ecosystems, and has a high probability of not being stable. That is to say, the Earth system will reach these tipping points. This is Dr. Rachel Warren from the University of East Anglia. She studies the impact climate change is having on agricultural systems. She says, we have already observed impacts of climate change on agriculture. We have assessed the amount of climate change we can adapt to, and there's a lot we can't adapt to even at 2 degrees. At 4 degrees Celsius, the impacts are very high, and we cannot adapt to them. The World Bank wrote this report a few years ago, saying that there is no certainty that adaptation to 4 degrees world is possible. A 4 degrees world is likely to be one in which communities, cities and countries will experience severe disruptions, damage and dislocation. With many of these risks spread unequally, it is likely that the poor will suffer most and the global community could become more fractured and unequal than today. The projected 4 degrees Celsius warming simply must not be allowed to occur. Okay, must not be allowed. So if I was to summarize all of that together into one statement, I would probably say the same thing as Professor Stephen Schneider. The bottom line is that you've got to adapt to what won't get mitigated, but you have to mitigate what you can't adapt to. And by mitigate, we mean reduce and phase out fossil fuels in this case. So to summarize, I'm going to use the kind of the Greek myth of Daedalus and Icarus. Okay, so Daedalus and Icarus were trapped in a prison and they wanted to escape. And so they came up with an ingenious plan. They used their human ingenuity to design these wings from the feathers of birds and wax that they had from candles. And they were able to take off from their prison and to fly into the air. And they succeeded and they were able to fly away. And Icarus was so taken with the fact that he could now fly that he started to go higher and higher. And his father, Daedalus, he warned him. He said, Icarus, don't go too high, because if you go too high, the sun will melt the wax in your wings. But Icarus kept on going further and further and wanting to go further. And in the end, his wings fell apart and he plummeted and drowned in the sea. So I think there's a lesson here for us still today that, you know, we have come so far. I spent a lot of time talking about the amazing progress that we have made as a human species, as a human race. And we've used our ingenuity to solve these problems in the past. And yet, we've now faced with a choice. All right? We're facing limits on what we can and can't do. And will we choose to ignore those limits and, as a result of that hubris, suffer a downfall? Or will we heed those limits and, like Daedalus, be able to continue to fly and use those powers to get to, you know, a new type of freedom? But it's clear, I hope that you'll agree, that we must change. Okay? And the question that we need to ask ourselves is, can we change? And that's the question that we'll be looking at in next week's lecture. So I hope you can all join us then. But in the meantime, I'm happy to take questions on what we've talked about today. So thank you, everyone. Thanks very much.